So we just looked at a system where I was able to convert that system to polar coordinates. And from there, we were able to see a periodic solution that was like a periodic steady state. But now I want to understand, when do these periodic solutions exist in general? So I'm going to consider the system of differential equations dx dt equals f and dy dt equals g. And our first theorem says, suppose that f and g have continuous partial derivatives on the domain D. A periodic solution or closed trajectory of the system must necessarily enclose at least one critical point. If it encloses only one critical point, the point cannot be a saddle. Okay, so let's look back at our system that we were just looking at and notice that there was one critical point, right? 0, 0 was a spiral source. And so that's not a saddle. So our theorem holds here that our periodic solution, which is the circle of radius 2 that you see there, okay, that must contain a critical point. That point is 0, 0. And that critical point cannot be a saddle, which it's not. It's a spiral source. Okay, let's move on to another theorem. It says, suppose that f and g have continuous partial derivatives on that simply connected domain D. If fx plus gy, so that's the x derivative of f and the y derivative of g, that would actually be the divergence of the vector field fg, has the same sign throughout our domain D, then there's no periodic solution of the system 1 that lies entirely in that domain. So we're going to look at a system that we believe has no periodic solutions. dx dt is going to be labeled as f, and dy dt is labeled as g. The x derivative of f is 1 plus 3x squared. The y derivative of g is going to be 2 plus x squared plus y squared. And when we add those two together, we're going to get 3 plus 4x squared plus 4y squared, and that is always positive. Does not matter what x and y we plug in. Since that does not change sign, this system has no periodic solution. So that's great that that theorem helps us understand when a periodic solution does not occur, but what about when a periodic solution does occur? That brings us to the Poincaré-Benedictson theorem. This theorem says, suppose that f and g, our right-hand side of our differential equation, have continuous partial derivatives on the domain D, and let R be a closed and bounded region inside D that does not contain a critical point of our system. If there exists a time such that a solution, x being phi of t and y being psi of t, exists and remains inside R for all t greater than t0, then either that is a periodic solution or it spirals towards a closed trajectory as t goes to infinity. In either case, the system 1 has a periodic solution in R. So this gives us a way to see if we have a periodic solution inside of a domain.